Okay, in this example here, we're going to do a quick introductory example to ideal transformers and show how the dot convention can affect things. And then we'll do a more complicated example to illustrate how we can solve these problems here. Okay. So first off, let's go ahead and write down what we're asked to find here. So we're going to be asked to find V out and power dissipated by load, which the load is just that 1 kilo ohm resistor, and power generated by source. Excuse me. Okay, so I purposely did this problem, and I'm going to do another example with these dot conventions like this. Now, if you remember in the previous lesson with ideal transformers, we had the dots and the coils both at the top. And then we had plus minus V2, plus minus V1. Then I1, the arrow was going into the dot. And then I2, the arrow was leaving the dot. And that's important because the equations we got here were that V1 over N1 is equal to V2 over N2, and that I1 N1 is equal to I2 N2. Now, some text will go ahead and discuss that depending on where the dot is, these equations might be negative. There might be a negative thrown in here or a negative thrown in here, or in both cases, or in one or the other. And when I was in college, I found that very confusing. The easiest way I find to do things is just look at the dots the way we drew it to develop the initial set of equations, and then just always draw my voltages like that when I'm working on a problem. So for instance, I'm going to draw a plus minus V1 here because I put the plus at the dot, and on the left hand side the current is entering the dot. So I got a current entering the dot. The arrow's going in. Now on the right hand side, notice that the plus is still at the dot. So I'm going to write this as plus minus V2. And then that the current is the arrow coming out of the dot. Like that. So we're doing that so that all of our signs are going to be correct on our final answers. But then what we can clearly see here is we can see that V2 is, I'll put in quotes here, parallel to the 1K, V out. I mean, it is in parallel, but we have opposite signs going on here. I have a negative at the positive terminal and a positive at the negative terminal for these two voltages. But they're essentially the same. They're the same magnitude. So what we can say is that V out is simply negative V2. So if I can figure out what V2 is, I can figure out what V out is, and then basically be able to do the rest of this problem here. Okay, so now we're going to go ahead and use my ideal transformer equations. On the left-hand side on the primary coil here, we can clearly see that that V1 and that voltage source are in parallel, and the plus and minuses line up. So V1 is simply equal to 115 and angle of 0 degrees volts RMS. Which then we just go ahead and use my turn ratio equation, that V1 over 10 is equal to V2 over 1. So I have 115 and angle of 0 degrees over 10 is equal to V2 over 1. In other words, this is similar to what we did in our previous problem here, I think. V2 is equal to 11.5 degrees, volt RMS. Now we're asked to find the power dissipated by the load. Now there's two ways we could do this. Of course, we could just say, well, power dissipated by the load, it's simply a resistor, so my power is P, and we could say that it's V out squared over R, or we could do V out times the current that I'm going to find here. Now, one thing I should maybe be careful of here is my answer here, and I put degrees there for some reason. It's volts RMS at an angle of 0 degrees. Volt RMS. One thing I made a mistake here is we're asked to find V out, and we had already written here that V out is equal to negative V2. So my final answer for V out is that V out is negative 11.5 at an angle of 0 degrees. Or another way you can write this, either answer is acceptable. You can still write this as a positive number, but then that negative gives it a phase shift of 180 degrees. So both answers are acceptable, except we would, of course, want to make sure to put units on them. So now the power, we'll go ahead and just use the voltage squared over R. So my power here would be negative 11.5 squared divided by my resistance, 1 kilo ohm. Let me just go ahead and pull up a calculator here. I don't have my calculator sitting next to me. So we had 11.5. I know it was negative, but I'm squaring it, so it's not going to matter. And then divided by 1,000. So we get 0.13225 watts, which we could, of course, write as 132.25 milliwatts. Now, the last part we're asked is to find the power generated by the source here. Okay, well, we have to look at what the current here is. I have 115 volt, but I need to know what I1 is. Well, there's nothing I can do on this side of the coil here, on the left-hand side, on the primary winding side, to find I1. I don't have any kind of resistor, because I can't say, oh, it's, the voltage, it's this inductor, the current, it's V1 divided by the inductance here, because this is an ideal transformer, so, we have an infinite inductance, and that doesn't mean you have zero current. So what we really want to use is we want to use our relationship for I2 and I1. We want to use this relationship here. But in order to do that, of course, we have to find I2. So I2, well, I2 is going into the negative side of the voltage source here. So we have that I2 would be equal to negative V out over 1 kilo ohm. Because it's going, the arrow's pointing into the negative side of that resistor. That's why I get this negative popping up here. And so if I do that, I get I2 is negative 11.5 at an angle of 0 degrees divided by 1 kilo ohm, which gets me 11.5 milliamps at an angle of 0 degrees. Oops, sorry about that. All right, so now we have I2 and we can find I1. We're saying, well, I1 N1 is equal to I2 N2. So I1 times 10 is equal to I2 times 1, which of course means that I1 is equal to I2 divided by 10. Well, that's easy to see then, that I1 is going to be 11.5 milliamps at an angle of 0 degrees divided by 10. So we get just simply 1.15 milliamps at an angle of 0 degrees. Now we're talking about power being generated by the power supply. First off, remember we say it's negative because it's generated, but you can see that because where's the arrow? It's coming in on the negative side of that power supply. So that means if I do voltage times current for the power, it would be a negative because I'm coming in on the negative side, voltage times current. And so my voltage, of course, is 115 and an angle of 0 degrees. And then my current is 1.15 milliamp and an angle of 0 degrees. And then if I do that computation, I wind up with negative 132.25 milliwatts. Now we shouldn't be surprised by that because we've said before here, because what's being dissipated on the load, the exact same thing is being generated. Now we shouldn't be again surprised by this because we say, well, you know, power has to be conserved on these two sides, and we said, well, if the voltage goes down, the current goes up. And we can see that the voltage went down by a factor of 10, but the current in the secondary coil is 10 times bigger than the current in the primary coil. But we do have the same power. Now, of course, we made one huge assumption here, which is unreasonable. I mean, that you'll never get a transformer to be like acting like this. Is the assumption, of course, we made is that there are no losses in the transformer. Which is 100% inaccurate. And as far as, you know, real applications, you might say, well, if it's 100% inaccurate, why do we bother with this? But again, in the previous video, I say the reason we kind of bother with this is that you can then look at a transformer and get a rough idea if you see the turn ratio, oh, 115, I'm going to get 11.5 on the output. Now, of course, this is assuming that there's no loads on the source or there's no additional load on the output. So we're going to look at one more example here regarding this that's a little bit more challenging, and we'll see what happens when we do that.